So, Mr. Demetrius, we've been talking about covalent bonds. That's the bonds where they share electrons. We want to go deeper with that. What's our next step?
Well, what if we want to, all the molecules around us don't just exist of one atom attached to another. We have multiple atoms attached to each other. One of the hardest things to do is to put them together in molecules until now. So the way we do this is by drawing Lewis structures, but we're not going to draw Lewis structures the old-fashioned way. Instead, we're going to draw it using the...
There's a simple strategy called the Kelter Strategy by, I guess, Mr. or Mrs. Kelter. I don't know who it was. They kind of came up with this crazy easy... Now, Lewis structure is like drawing what the atoms look like with all the bonds. Remember we had the double bonds with oxygen and Mr. Brinkelhoff and all that stuff that we learned in the last video. Now we want to do is draw some other ones. So what are the steps to the Kelter Strategy?
So you guys have in your notes the steps in front of you, and you can see them here on the screen here. We're going to have these at your hand at all times.
But I think it's important to talk about the periodic table first, right?
Yeah, so what we're going to do, though, is this. I'm going to give you a structure here, but before we do that, we need to be able to track how many valence electron each element has. So if you remember way back in the day, we said this. Everything in group 1 has 1 valence electron. Everything in group 2, 2 valence electrons. We skip this middle block here, and then we go over here and we have 3, 4, 5, 6, 7, and 8. Helium is kind of a spy. It really belongs over here, and it has 2 valence electrons. Why is that important? Because part of our strategy is going to be to track the number of valence electrons that the atoms bring to the party.
So the step 1 in the Kelter Strategy is what?
Count the valence electrons.
So let's do an example. I think this is going to help us a lot better if we do this. So
Yeah.
number 1, you want to count the valence electrons. So what example?
We're going to use CO2 as our example.
All right, so with CO2, I want to count the valence electrons. So I come back over here, I want to find carbon. Now carbon is 1, 2, 3. He's in the 4th category. And oxygen, or 4th column, there's 4 valence electrons, and oxygen is 6. So I got, in my head, 4 and 6.
Yeah, so when we add it up, and we have a little table on the side here, we're going to go valence, and if you see here, I'm going to go valence, happy, and number of bonds. And this is the secret to doing this. We're going to do these 3 steps always, until you can do it in your head. But valence, we just figured it out here. We had 1 carbon, and that carbon had 4 valence electrons.
But now oxygen were 6, so, and there's 2 of those. So,
So
6
we have to
times
add
2
that
is 12.
to 2 times 6, and then altogether, if we add them up, we have
12 and 4, 16 electrons.
16 electrons.
All right.
Now, happy is kind of weird because it's not a thing. And if you go talking to your professor down the road and you're like, yeah, does it have a certain number of happy electrons? But here's what we do. We understand this. Don't atoms want to have a full outer shell?
Which is 8. Right?
Yeah,
They
so
want to have 8 electrons.
every atom on the periodic table wants to have 8 electrons to be happy, except for, and this is really important,
Hydrogen.
the first 5 on the periodic table. 1, 2, 3, 4, 5. The first 5 on the periodic table, they want just 2 to be happy. So what we're going to do is we're going to play the game that's not really a game, it's certainly not fun, and it's going to be which one of these is part of the first 5 on the periodic table. And the way you win that game is by saying none of them are the first 5.
It's not carbon. Carbon is not hydrogen, helium, lithium, beryllium, or boron.
So all 3 of these are not part of the first 5.
They all want 8.
They all want 8. And so we can do the math really quickly. We can say all 3 of these want 8, so we can just go 3 times 8 is 24.
Got it.
So if you ever talk about how many happy electrons there are, we're just saying how many does each atom want altogether to be happy. Now that allows us to do this neat little trick. For the number of bonds, what we do, we take the happy minus valence and we divide by 2.
So happy is 24 minus 16, right? You want to write that down.
24 minus 16 divided by 2. And if you go 24 subtract 16,
That's 8.
8 divided by 2,
That's 4.
that's 4. That means that we are going to put this structure together, this carbon, this
4
oxygen.
bond. Now the question we got to ask though is, it's CO2. Which one's on the inside and which one's on the outside? Is it COO? Is it OCO? Is it whatever the options are?
Yeah. So all things being equal, molecules like symmetry. They like to be arranged. So of the COO versions, they probably aren't going to work. But here's a better thing. If you take a look at your notes, we say this. We're going to build a skeleton structure, because if you're going to build anything out, you always want to start with a skeleton. Always put carbon in the middle. If we don't have carbon, take the less electronegative atom, and we'll deal with that when we get to it.
Another thing to know is almost always we're going to put the first letter will be the central atom, right?
So in order to do our structure, we're going to put carbon in the middle, and we know around the outside we have to have 2 oxygens. We're just going to lay them out like
So
this.
C is the middle atom, right?
Middle atom.
And we got to put some bonds.
Yeah, so we have to attach them, and the very minimum number of attachments, then we have to attach each with 1.
Got to have at least a single bond. Now remember, what is a bond? A bond is 2 electrons. A single bond is 2 electrons, right?
1 for each one.
My total is 16, right?
That are being shared. Now, here's the thing. Normally, and this is where the Kelter method really shines, we'd be like, well, what do I do from here? Well, here's the thing. Once you have your atoms attached, we look at the number of bonds you're supposed to place. We have 4 bonds to place. Now there's a couple ways we can do this. Couldn't we do this? My fingers represent bonds. Couldn't we do a double and a
You
double?
go 2 and 2, or you can do 3 and 1,
3
or
and
1
1,
and 3.
or 1 and 3.
It's better to go 2 and 2 because 2 and 2 is more balanced, okay?
So we're gonna go 2 and 2.
That's not 100% true, it's close.
So right now we have our skeleton structure. All the bonds have been placed. Our question is now, how do we make each of these atoms happy? So
Well, carbon's already happy because remember a bond counts as 2 electrons. So 2, 4, 6, 8. He's already got 8, so he's a happy camper.
yeah, so we say this step that we're following after we attach everything, we say complete the octet or duet. So that means make sure that every one of these has 8. Now, as Mr. Bergman just said, we have 2, 4, 6, 8. This guy right here,
He's happy.
He's happy.
But oxygen isn't because he's only got 2, 4. Because he's sharing these 2 pairs of electrons. A bond is 2 electrons. He needs more. So, but we still got more to spend. We have total. If you think about it, we had $16, and we got to spend every dime. All right. So I've got to now put the electrons elsewhere. So how would you indicate that on say the oxygen on the
So
right
what
here?
we do right now is this. Since the bonds have all been accounted for, we're only allowed to have 4 bonds. The method does not lie to us here. We need to then draw what we call lone pairs of electrons. And we draw electrons in pairs because that tends to be how they exist. So if I have 2, 4 here, doesn't that mean I need another 4 to...
Put some more on the outside.
So the way we do this, I'm going to put 2 here and 2 here.
Yep.
And you may think to yourself, well, why did you choose there? Well, you could, if you're like being contrarian, you could go like this. But typically we like to do it this way. We don't like to see this. And I don't know why it is. Maybe you can explain why this is not the greatest. I mean, it's not wrong.
Yeah, but it actually is because the atoms, or the electrons, pardon me, are getting into the orbitals, and you can only have 2 electrons in an orbital, so that's why they're putting in pairs. And if you look at him, he's got 2, 4, 6, 8. He's happy. Now, if we do the same thing to the oxygen on the outside, he's got 2, 4, 6, 8. Now, let's make sure. Have we added up the total number of electrons?
Yeah, and this is actually what he's saying right now is a really big deal. So we made 8 around each one. That's super great. But what Mr. Bergman is saying is this. Didn't we have 16 electrons to
We've
start
got to
with?
spend 16. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Oh, check. So that's it. That's the answer. So let's do like the crazy, probably easiest molecule, most important molecule in the world, which is water, H2O.
And here's where we have to be careful about a couple things here. Because remember in the last example, we mentioned, well, the first thing always goes in the middle. That's not how it works.
In this case, yeah, it's not going to be.
So here's how it actually works. On the periodic table, if we have carbon, we always use carbon in the center. But if we don't, remember we talked about electronegativity. Fluorine is the most electronegative atom on the periodic table.
He's the strongest one. He wants the electrons the most.
And here's what's really important. The least electronegative atom that can attach more than one thing, it goes in the middle. So fluorine would be the last one you put in the center. We go away from it, and the farther you are away, the more likely it's to go in the middle. Now, you may be thinking in this case here, well, wait, hydrogen could go in the middle. Hydrogen's unique because hydrogen only has 1 electron. Now, in order for me to share with you,
Hydrogen has always been the outside because he's only got 1.
it's got 1 attachment.
He's one of those guys who wants 2.
Yeah, as soon as I attach once, I'm done.
Yeah.
So never put a hydrogen in the middle.
So-
in this case, oxygen is going to go in the center.
So you put O in the middle there.
But here's what we're getting ahead of ourselves. We're starting to draw the structure without having done the method.
Well, I think we can do it. We can write the H's and then we'll do the method. There's going to be an H and an H, at least there. But let's go ahead and back to Kelter Strategy. So we got how many electrons total we have? Hydrogen, remember he's in column number 1. He's got 1. Oxygen, we did this just in the previous example, he's going to have 6. So it's just going to be 2 plus 6. Right? Because there's 2 hydrogens at 1 plus 6. That's just total of 8. We get total of 8 electrons.
Now, the happy trick here, and this is
yeah.
where we deviate. So if we play the game, which ones are part of the first 5? Do you see how hydrogen, 1, 2, 3, 4, 5, isn't it part of the first 5?
Number 1, yeah.
So in that case, it only wants to have 2 to be happy. So if we take a look at this, it's going to be a little different than the previous example because these 2 hydrogens, both of them, they're going to want to have 2 to be happy. This oxygen is not part of the first. And by the way, when in doubt, say 8. Because the majority of times, the majority of the periodic table wants 8 electrons. We're going to go plus 8.
And there's only 1 oxygen, so therefore it's only 1 times 8.
So we have 8 and 12. Now, if you remember for the number of bonds, we always go
12 minus 8.
happy minus valence. So we're going to 12 minus 8 divided by 2. And if you do the math on this, it's going to tell you you need 2 bonds. Now, Mr. Bergman, knowing this in advance, jumped the gun on this and put the bonds in here, but I just wanted to do proof of concept here. It tells us we need 2 bonds. That means you're not going to be trying to do a double bond or a triple bond. We're done with the number of bonds.
So now we still need to check and see if everyone's happy. Now the hydrogens
We love hydrogen.
are already happy because if you got a bond, they're happy. They want 2. A bond is 2. They're happy.
So each of these hydrogens has 2 around it.
They're
How about
happy.
this oxygen?
He's unhappy because he needs 8 and he's only got 1 single bond on either side, so that's 4. So he needs more.
He needs 4 more.
So he needs 4 more. So we're gonna put 4 more and they have to go on the oxygen.
Now, the way we picture this here is we always picture it like there's a square around this, and we want to put maximum 2 on a side.
Yeah.
Now I'm going to remove this because I don't want you drawing squares.
Let's check the oxygen. Oxygen has 2, 4, 6, 8, right?
Yep.
2, 4, 6, 8. So he's happy. Everyone's happy. Check.
Everyone's happy. The other check we have to do all the time is, remember, we brought 8 electrons,
Oh, yeah.
8 coins to the table, right? We can only have spent that. If we have only spent 6, our structure isn't any good. If we spent 10, how do we make a structure with more electrons than we brought to the party? So if you do the math, 2, 4, 6, 8,
And matches.
it matches. This is a great structure.
All right, we're going to close this one out with one more difficult one. This is nitrate. Now, if you recall from your polyion table, nitrate is NO3 with a -1 charge. So something weird with this -1 charge.
Our valence, our happy, and our number of bonds, they're all the same.
So we've got N and O. So let's just double check our periodic table. Nitrogen here is in column 15, so it's 5.
1, 2, skip the middle block, 3, 4, 5.
By the way, if it's column 15, 5.
Subtract 10, yeah.
Subtract 10. And 16, and O is 16, or 6. So we've got 5 and 6, but we've got different numbers.
So nitrogen has 5 valence electrons, so we're going to go 5. Each oxygen has
3, or 6.
Six,
There's 3 of
and we
them,
have
so
3
3
of them.
times 6.
But there is one
What do you
thing.
do with the -1? Remember, if you have a charge of -1, that means you have, now, it's a little tricky, 1 more electron. -1 means you're adding an electron. So a -1, you just add 1 electron. It's just +1.
So the only place that this impacts us, the only place is right here in the valence.
If it was -2, by the way, if this, because you'll be given one of those, you're going to add 2 electrons. -3, you add 3 electrons, etc.
What about if we ended up with a plus?
Then you subtract electrons.
So this right here, and this is really important, the only step that this impacts us is in this first step. Other than that, we do everything like normal.
So let's add that up. So that's 18, 19, and 5 is 24 electrons.
Now, you're going to know that you've done wrong if you end up with an odd number
Yeah,
of
you can never have
electrons.
an odd number, by the way. And so the happy, we want to figure out the happiness. So the N and O are not one of the first 5, so they all want 8.
They all want to 8, and there's
So
4 of them,
there's
right?
8 times 4, 32.
Yeah,
right?
so I tend to just group them together and go, there's 4 of them, they all want 8, that gives us 32. And remember, our adding for our happy, or for our number of bonds is always
32 minus 4, 24, right? Divide by. Now, what we're going to do is we're going to draw our structure. We're going to have 4 bonds. Now, which one is the central atom?
Yeah,
Now,
and-
we want symmetry. You got 3 O's.
Yes.
But also, the rule applies.
So fluorine's the most electronegative atom. When you look at it,
Oxygen is still pretty electronegative, but nitrogen is less.
of the 2 of them, nitrogen is the
Yeah,
least.
yeah.
Mr. Bergman hit on something here. When in doubt, we go symmetrical. If you have one thing and 3 things, chances are the one thing is going in the middle. But more importantly in this case, the N is farthest away from the fluorine.
Yeah, yeah.
So
N-
I'm going to set this up, and at the very least, don't I have to attach these 3 oxygens around
Yeah,
it?
got to at least have a bond between the N and the O, so that's going to be 3 bonds. But here's the bugger. If you recall, we needed 4 bonds. So we just, now, where do you put it? Now, at some level, it's N to O. They're all the same, right?
Yeah.
So you can pick any O, and
And by the way, I did this right now, and you may be going, well, why did you decide to make this T-shape? It doesn't matter. I'm going to do this right now. Wait for it. This here is the exact same structure. If you were to flip it on its side, it looks exactly the same. It doesn't matter how you set them up.
Just put a bond on one of
We
them,
put a
randomly.
bond, pick one of those 3, they're all identical.
They're all the same.
So let's just say I decided I go here, we can go on from there. Now, we always want to make octets in the next step, right?
So 8's our magic number. So I'm going to start with N because he's the one in the middle, and then I go from the outside. So 2, 4, 6, 8. So N is happy. He's a happy camper.
Make a little happy face here.
All right, and then the
Which one?
O's are unhappy, but they're actually different. Bottom O guy, he's got 4, so he needs 4 more.
Again, let me remind you, 2, 4, so we're going to go
6,
6,
8.
8.
Okay, but this bad boy up here on the left, he's only got 2, so he needs 3 more pairs.
So we're going to go with 6 right here.
Notice how you put 6 there, and of course it's the same on the top one. Now, we've got to double check if this is correct. If we've got the same number of electrons, which is 24. So let's just add them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24.
So this
Bingo.
structure is really good, but we're not done here, and this is really, really important to keep in mind. We've got to acknowledge that this guy right here, an extra electron snuck in here. And the way we do that is we put the entire molecule in these big fat brackets,
Big squarey brackets.
squarish brackets, and then we put the charge on the outside.
Yes, you put -1 or minus charge right there. So if you ever have a polyatomic ion, and you will, when you have a polyatomic ion, you have to do brackety and then charge. Put -1, -2, +1, whatever the charge is, bracket, charge.
We've got to identify that this is something that's a little bit weird.
So that's how you draw Lewis structures. You use this Kelter strategy, the bonds, subtract, all that stuff that we've been talking about. And you're going to get a lot of practice in class because we've got, I don't know, 20 of these for you to do. I don't know, something like that. And you're going to, it's easy. But it's cool too because you're designing molecules that actually really exist and are important for living, important for the universe, etc.
So bear in mind that if the first time you're like, I don't get this, we're going to practice and we're always here for you. See you next video.